So, hello everyone, myself Nagmani Kumar and I am going to present our advanced data structure and algorithm project in front of you. So, our topic is data structure in web information retrieval. So, here we will see how data structure is used in the search engine and information retrieval to retrieve document very efficiently. So, let's see. So, our team member consists of Pankaj Yadav, Narayan Jat and me, Nagmani Kumar. So this is the table of content where we will see in the upcoming things. So first is introduction, inverted index, then index compression, fingerprints, finding near duplicate documents, and then conclusion. So let's go on the introduction part. So you may see that whenever you search for any query on Google or Bing, then just below the query section you may see that there is a section where this is written that about 12 million or 12,000 documents in 0.5 seconds. So this shows that nowadays how much search engine is efficient and they are distribute document, relevant document for us in very less time. So this is only because of two things. One is massive parallelism in the search engine and another is efficient data structure be used in the search engine. So let's talk about massive parallelism, means how this work to extract relevant document efficiently. So in parallelism what we do, we have let's say we have billions of documents. Then what we do, we will take 1000 parallel machine and we will give 1 million document to every machine. Then that machine run on a query and that query every machine will take top 10 relevant document and then send to the central machine. So the load of all the machine will be less and very efficient. They will find the document from the million document. But if one machine can do find relevant document from the 1 billion document, then it will be very inefficient. That's why we use parallelism, so that we can extract relevant document very efficiently. So we know that parallelism means we have to divide task in the smaller subtasks so that we can take things efficiently. So another thing is data structure. So here we will use inverted index for search engine. That will be explained by the Pankaj. And the another is duplicate detection using fingerprint. Means whenever there is a user and if you show the duplicate web page to them, then they might be you might lose that users. So to delete duplicate, we use fingerprint, and we will see in the upcoming slides what we will do. So over to Pankaj.
So now let's talk about the inverted index. So inverted index is used in to retrieve the relevant document efficiently in a web search engine. So in this slides we will learn about the how we use inverted index to retrieve the relevant document in search engine. So first I will talk about the what is the inverted index and how we will implement inverted index data structure. Now we will talk about why it is called inverted index and what are its challenges. So let's get deep and dive into the inverted index. So inverted index, what is inverted index? Inverted index is a data structure which is used in web search engine to retrieve relevant document in a quick way, efficiently. So let's we have a user queries which contains t1, t2, t3 till tn is index term, and the goal of the search engine is to retrieve the relevant document that contains the same index term, and their document score is very high to rank the web page to the top rank. So what we will do, so the structure of inverted index data structure is we have a key as an index term and it is pointed to all the documents that has the position of the index term and frequency, word frequency of the index term, as well as the document frequency and inverted index frequency of the inverted index. So we store in the documents. So next slide so here is the motivated example of the inverted index, how the inverted index data structure used to store the index term, and how it retrieves the document in access in very quickly. So we have three documents, doc1, doc2 and doc3, and they have some text, and now the goal is to retrieve the documents in a very efficient way. So first, we will what the search engine do. First, it filter and tokenization process happen. In filtering, we remove all the stop words from the document and send it and store the for the each index term we store the inverted list, corresponding inverted list. In inverted list we have a document ID, position of the index term, and and term frequency of the index term. So here is the we have first sort all the index term on the basis of alphabetical order, and here is the index term is the key as apple. Apple is a key index term, and it is stored in the document 3, and its frequency is 5, and its position is 6, and so on. Now let's move on the talk about the how we build the inverted index data structure. So first, what we will do, we sort all the index term using sorted tree and store in the sorted tree or hash function. So we can use also merge sort algorithm to sort all the index term in alphabetical order. Now what happens when we sort all the index term, and now our goal is to store in inverted list. So if you see that web search engine has millions of index term, so that will create a large array of inverted list. So we can't store the large array in a single machine. So we requires a lot of money, a lot of machines to store the inverted list. So for this we use RAM or disk. If you take an example of Google search engine, it has a data center. In data center, they have it has lots of RAM processor and disk where it store all the large array of web search engine web page. Now we will discuss the challenges of inverted index while storing the index term. Since we have a large array of inverted list, so of course there will be the problem of storing purpose. So what happens, first we determine the all the documents containing the query terms. To do this, we do parallel computing. We search parallelly on the each index term corresponding the inverted list, and take the intersection of the documents and give to the users on the basis of document score. Those documents have a highest document score, we keep to the user as a top web page rank. So there will be a problem occur when some query have a negation like if a document have a text like dogs are barking, and some users type it in as a query dogs are not barking. So not barking is the negative of the index term. So for this we use another inverted list. So to do this we needs a lot of computation, and for doing this it slow down the computation. So for handling this type of problems we use index compression, and this index compression will be described by the Narayan Jat. And over to you, Narayan.
Hi, my name is Narayan, and as my friend Pankaj Yadav discussed the challenges of the inverted index. So there are many ways to handle those challenges, like Magni talked about the parallelism, and I'm gonna explain the index compression. So basically we will reduce the size. So these topics I will cover. So first of all let's know what is index compression. So basically, as name suggests, that is the compression of the inverted index, with the large size inverted index. So and of course, why is it required? So as we have faced, the challenge was that storing it. Since the inverted indexes are very large, so storing is a problem. So compression will of course help us to store it efficiently. So now third point we will discuss is how it affects information retrieval. So of course it may delay information retrieval, like, because if we are doing compression, then we will apply some encryption and compression algorithm, and we have to also decompress. So this compression and decompression will little bit delay the information retrieval, but it will be beneficial in storing the inverted indices, right? What are its challenges? So challenges are like it requires more CPU cost, not memory, but CPU cost required, because and most time because in compression and decompression will be going on, right? And So how do we perform it? There are many algorithms for the compression, like delta encoding, v byte encoding, and many more. But I'm gonna discuss delta encoding. Right. So this is delta encoding. So what we do in inverted indices, we store document IDs. Now document IDs are very large in size. Like you can see the IDs are like 10002, 10007. This we are storing 100 many times. So rather than this, what we can do, we will store the first ID as it is, and then in subsequent we will store the differences of two consecutive IDs, and then so on. Like differences of 1002 and 107 is 5, and 108 say 1 3, like that. So the differences will be small. The IDs are bigger, but differences will be small. And if we want to get again document ID from these differences, then we will go to the any difference, and to get the ID of that difference, we will just sum earlier, or we will just get cumulative sum of all the previous differences. That will give the document ID of that, right? So this is a very simple algorithm, delta encoding. Right. Now other major issue in the web information retrieval is that duplicate. Now duplicates are found in like copies, plagiarism, versions, and etc. So we have to detect like 30% of the web is containing the duplicates, and duplicates of the 70% of the rest. So why duplicate is a problem, right? So well, because if we are gonna show the results to the user, and if we have ranked top 10 documents, and if the many of them are similar, then user will get bored. Like he or she might not be interested in our search engine, right? So to prevent users from getting bored and duplicates, also if we found some duplicates and we will remove duplicate documents, then it will of course help us in reducing computational power, right? It will reduce computations for further processing. So in that way it is helpful. Near duplicate and exact duplicate. So the problem is with near duplicate. Basically finding near duplicate is hard than exact duplicate. In exact duplicate we will just check word by word and we'll match. And if it is the exact matching, then it is exact duplicate. But there are many algorithms deployed for finding near duplicate, and they like clustering, blocking, and fingerprinting many. So I'm gonna explain fingerprinting algorithm. So what is the fingerprinting? We will have a document text. First we will tokenize them. Then after that we will apply some like we will make groups of the text, some index terms like n-grams, right? After that what we will do hashing, like hashing of that by some algorithm. And to reduce the size of hashing, like hashing will be a vector, right? So we will further apply some algorithm to reduce the size of the vector, and then we will have one vector for one document. And if the two documents are in the vectors elements in the two document vectors are matching, then the two documents are similar, right? So let's see it with an example. So we have the text like tropical fish include this original text, and this is the n grams. Well, we are having 3 grams, and this is the hashing, right? Hash values for all these documents. Okay. Now this is the further selected hash values using 0 mod 4. This is the 0 mod 4 technique, means whatever hash values are divisible by 4 will be chosen further. So 664 is divisible by 4, and 492, and these are chosen 4. Now this is the final size of the hashed vector. Now we will compare this with the vector of another document. Okay, and this was the fingerprinting algorithm. Now for the conclusion and for the further giving and I would like to invite Nagmani Kumar. Over to you, Nagmani.
So let's conclude our lecture. That is, so we have seen that we have presented dominated data structure for web search engine, which is inverted index, and we have also described fingerprints, which are useful in multiple places, like search engine, document sketch for near duplicate dissection. And one other thing which we have not described, that is a adjacency list, in which we use to we used to give the analysis of hyperlink structure, means how two pages are connected to each other. So that is also relevant in the case of web search engine. So finally we have presented all the things. So thank you very much. Thanks.